Hi, this is John Whitaker for the Probability 1 class, and this is our 12th video lecture. And last time we ended with talking about independent random variables. And what we had shown was that independence occurs between x and y if and only if the joint probability density or probability mass functions is equal to the product of each individual density or mass functions. And we're going to use that to test whether two particular random variables are independent or not. And we'll do two examples of that. So that's what we're going to start off with today. So here's examples I'm going to look at. Let's let f of x comma y be equal to 1 over 30 x squared of y, where x can be equal to 1 or 2, and y can be equal to 1, 2, or 3. And the question, well, first of all, let this be the joint PMF of x and y. And the question is, are x and y independent? Okay, so what I'm going to do is I'm going to compute each one of their probability mass function for x and for y and see if their product is equal to this joint PMF. So I'll start off with note, when I look for the PMF of x, remember what that was? That was the sum over all y values, and so here y would run from 1 to 3, of f of x comma y, which will be equal to, it's going to be 3 items. So it's going to be, when y is 1, we have 1 over 30 times x squared plus 1 over 30 times 2x squared plus 1 over 30 times 3x squared. And so when I add those together, that's 6 over 30 x squared, which equals to x squared over 5. Okay. Now, the PMF with respect to y is going to be equal to the sum over all the x values, so x runs from 1 to 2, of f of x comma y, which will be equal to, so it's 1 over 30, it will be 1 squared y plus 1 over 30 times 2 squared y, which is going to be equal to 5 over 30 y, which we can rewrite as just 1/6 y. Now note, the PMF of x times the PMF of y will be equal to, it will be x squared over 5 times y over 6, which is equal to x squared y over 30. And that is equal to the joint PMF. So that tells us that x and y are independent random variables. Okay. Now for another example, in the continuous case, we'll let f of x comma y be equal to 5/16 xy squared if, again, 0 is less than x is less than y is less than 2. And 0 otherwise. And then let this be the joint PDF of x and y. The question is, are x and y independent? Okay, well, again, we'll compute the PDF of x. And if you remember, that's the integral from minus infinity to infinity of f of x comma y, and then you integrate with respect to y. Now look, as I draw what f of x comma y, where it's non-zero here, so I draw this region, let's remember the x values and the y values can run from each from 0 to 2. But then we're only taking the region where x is less than y, and that happens here. Y is bigger than x in this triangular part of this square. So here's where we're integrating over. And if you'll notice, the x values can run to 2. Sorry, 2. That's what they can run from. So for any fixed x value, what do the y values go from? They go from, so this becomes the integral. The y values go from x to 2. And here this will be 5/16 xy squared, and then dy. And then that's equal to 5/16 xy cubed over 3, evaluated from x, from 2 to x. And then that's going to be 5/48. Here we're sticking it for y. That's going to be times x times 8 minus, okay, just enough room here. When I stick an x, I'm going to get 5/48, and then it's going to be x to the 5th. Okay? And so we'll simplify that just a little bit. So that's equal to, if you will, 5/6x minus 5/48 x to the 5th. Okay? So that's what PDF of x is. Now, the PDF of y is equal to the integral from minus infinity to infinity of f of x comma y dx. And again, let's not forget the area of integration here, the region of integration, I should say. And so the y values, they can run from 0 to 2. And for any fixed y value, the x values are going to run from 0 to y. So we have 0 to y of 5/16 xy squared dx. Okay, and then that's going to be equal to 5 over, we're integrating with respect to x. This is going to be x squared over 2, so it's 5 over 32 x squared y squared, evaluated from 0 to y. When I let x be y, what I end up getting is 5 over 32 y to the 4th, and that's it. Because when we let x be 0, we just get out 0. And so here, what I will just say, observe that f sub x of x times f sub y of y, that equals to 5/6x minus 5 over 48 x squared times 5 over 32 y to the 4th. Okay? And that does not equal 5/16 of xy squared. Okay. So they're not the same. And thus, we conclude that these random variables are not independent. And thus we call them dependent. Okay? Now, a fact that I want to look at that has to do with independence says if x and y are independent, then for any functions h and g, the expected value of g of x times h of y will be equal to the expected value of g of x times the expected value of h of y, and we're going to prove that. So here, note the expected value of g of x times h of y is equal to, well, it would be the double integral from minus infinity to infinity, minus infinity to infinity, of g of x, g of y, sorry, h of y, times the joint PMF here. So here I have, I'm sorry, you know, I should back up for a second. That's what we would do if they were continuous. But let's start off, sorry. Yeah, let's do the continuous case, but let's start off with let x and y be independent. Excuse me. Be independent. Random variables. Okay, and so we are going to do the case where we have them being continuous. So what I had written was part of what we're going to look at, but I just wanted to put that setup of assuming the independence. And I think if I'm going to have case one, if x and y are jointly continuous, then, as we had written before, the expected value of the quantity g of x times h of y will be equal to the double sum from a double integral from minus infinity to infinity, minus infinity to infinity, here of g of x, h of y times the joint p df, f of x, y, dx, dy. That's where we are. And then that's going to be the double integral, so from minus infinity to infinity, minus infinity to infinity. And here, this x should be a little x, this y should be a little y, make a mistake. This is g of x, h of y. Here, because of independence, the joint can be written down as the product of each individual. Okay. Now, with respect to the integration, with respect to x, this are constants, if you will. So what you could do is you could bring them outside the integral and have minus infinity to infinity. Here's h of y, f sub y of y, and then integral from minus infinity to infinity, g of x, f sub x of x dx, and then dy. When you do this integral, integral, minus infinity to infinity, h of y, f sub y of y. This is nothing more than the expected value of g of x, which is going to be a constant, dy. So it can be pulled out, and you're looking at e of the expected value of g of x times this integral from minus infinity to infinity of h of y, f sub y of y, dy. That's what we're looking at. And of course, this last integral is the expected value of h of y. Let me write that down. Which is equal to the expected value of g of x times the expected value of h of y. And that's what we wanted to prove in this case. In case 2, I'll just make a comment, and that's the discrete case. The proof is analogous to case 1. Except it involves summations instead of intervals. So I'm not going to do that, just write down that comment. As a definition, the next thing we want to talk about is something called covariance between x and y. And so this helps, in some sense, the covariance does, helps measure the interplay between the random variables. And here's what it says. The covariance of any two variables, x and y, is denoted by covariance of x comma y, and given by the covariance of x comma y is equal to the expected value of the quantity x minus the expected value of x times the quantity y minus the expected value of y. Definition. And then, as a fact, the covariance of x comma y is equal to the expected value of x times y minus the expected value of x times the expected value of y. So that's a fact. It's much like the fact we had about variance, and covariance is a lot like variance. So here, to prove this, let's note that the covariance by definition between x and y is equal to the expected value of x minus the expected value of x times y minus the expected value of y. And that's equal to, so if we multiply this out, it's the expected value of x, y minus x times the expected value of y minus y times the expected value of x. And then finally we have plus the expected value of x times the expected value of y. Okay, now the expected value of a sum is going to be equal to the sum of the expected values. So here, this is the same thing as the expected value of x times y minus the expected value of the quantity x times the expected value of y minus the expected value of y times the expected value of x plus the expected value of x times the expected value of y. And so that's equal to the expected value of x times y. Now the expected value of y here is a constant, so it can be pulled out. So you have the expected value of y times the expected value of x minus, here the expected value of x can be pulled out, and you'd be left with times the expected value of y. And here, this is just a constant. The expected value of a constant is that constant. And I'll write to conclude the proof in just a second, but here these are exactly the same. So we got minus 2 of them, and here's plus 1, so we end up with minus 1 of them. And that's exactly what we wanted to have happen. Let me write that up here. Which equals to the expected value of x times y minus the expected value of x times the expected value of y. And so that's our proof. Now I want to do some examples. And they're a little bit lengthy to do these examples because there's 3 things here if we use the formula for covariance to compute. But here's an example. If we let the joint PDF of x and y be f of x comma y is equal to 1 if 0 is less than or equal to x, is less than or equal to y, is less than or equal to the square root of 2, and 0 otherwise. Then the question is to find the covariance between x and y. Okay, here, let us look at the region where the joint PDF is non-zero, so that'll be our region of integration here, where we get something that's non-zero in terms of computing the expected value of x times y and expected value of x times expected value of y. So x can run from 0 to square root 2, so can y. So that's this square. And then we have the same x equal to y line to worry about, and where y is bigger is here. And so we'll start off with note the expected value of x times y, something we'll need. And by definition, the expected value of g of x of y, that's going to be equal to the double integral, so from minus infinity to infinity, minus infinity to infinity, of xy, f of x comma y, dx dy. Now, we don't know these are independent, or that they're not, but we don't need to know. We can compute this correctly. So that's equal to, so if we think back to where f of x comma y is non-zero, what we're going to be integrating over, so I'll write that, if you don't mind, I'll redraw that picture here. Remember, here's what we're looking at. Square root 2, this region here. And so here, this is equal to, okay, it's going to be xy, and then we have 1 dx dy. Let's think about it. Fix the y. What would the y values run from? They run from 0 to square root 2. Look for the y, what the y is. If you fix the y, the x values are going to run from 0 to this line, which is y, and that's what we have. This is equal to the integral from 0 to square root 2. Here, integrating with respect to x, I'm going to get x squared over 2. Y, that needs to be evaluated from 0 to y, because they're x values that we're substituting in for. Dy, that's equal to, here we're going to have the integral from 0 to square root 2, letting x be y, I'm going to have y cubed over 2 dy. That's going to be y to the 4th over 8. Evaluate from 0 to square root 2, stick in the square root 2 and raise it to the 4th power. Square root 2 times square root 2 is 2. Square root 2 times square root 2 is another 2. So we get 2 times 2, that's 4/8, which is 1/2. That's one of the three things we need in the formula to calculate the covariance. The next thing is I'll say note the expected value of x. Well, that can be thought of as the double integral from minus infinity to infinity, minus infinity to infinity of x, f of x comma y, dx dy. Which again, because of the way that the joint PDF is defined, this is going to be from 0 to the square root of 2, 0 to y of x times 1 dx, which would be equal to the integral from 0 to the square root of 2. This will be, should have dy here. This is going to be x squared over 2, evaluated from 0 to y, dy, which is going to be equal to 0 to square root of 2's integral. This is going to be y squared over 2 dy. When I integrate that, I'm going to get y to the 3rd over 6, evaluated from 0 to square root of 2, and that ends up being 2 times square root of 2 over 6, or just the square root of 2 over 3. So that's the expected value of x. Okay. Now, the last thing we need to do is find the expected value of y. And so that's equal to the integral from minus infinity to infinity, minus infinity to infinity of y times f of x comma y, dx dy. You know, I might be asking, how come that's what it is? I'm thinking of this as a function of x and y. G of x comma y is equal to y. And so that's how I get the expected value of g of x comma y, which is just in this case the expected value of y. That's going to be equal to the integral from 0 to square root of 2, integral from 0 to y of y, remember this is 1, dx dy, which is equal to, here this is the integral from 0 to square root of 2, the integral of 1y, or y, I think with respect to x, is xy. It needs to be evaluated from 0 to y for the x values, dy, which is equal to, here, this will be y squared, integral of that from 0 to square root of 2, dy, which equals to y cubed over 3, 0 to square root of 2 is where I evaluate from. That's going to be 2 times the square root of 2 over 3. Okay? So the covariance between x and y is going to be equal to the expected value of x times y, which will be calculated minus the expected value of x times the expected value of y. And we have numerical values for each one of these. So this is going to be equal to 1/2 minus, this guy was the square root of 2, I think, over 3. That was the expected value of x. Expected value of y is in there in front of me. It's 2 times the square root of 2 over 3. That's 9, it's denominator. Here's 2, common denominator is 18. This is 9 over 18 minus, I'd have to multiply this by 2 to get 18 for the bottom. Multiplying the top by 2, that's 4 times 2, that's 8. So we end up getting 1 over 18 as the covariance between x and y in this example. Let's look at another example. Okay. And so here, we're going to let f of x comma y be equal to x plus y over 21, where x is equal to 1 or 2, and y is equal to 1, 2, or 3. And the question is to find the covariance between x and y. Okay, so again, what I'm going to find is 3 things. The first of which is the expected value of x, y, x times y. So that's going to be a double sum. As x runs from 1 to 2, y runs from 1 to 3. Xy times x plus y over 21. So when x is 1, we're going to get, and then y starts running from 1 to 3. We're going to 1 times 1 times 2 over 21 plus y, x is still 1, so it's 1 times 2 over 3, times 3 over 21. Plus, now when x is still 1, y is 3, so it's 1 times 3 over 4 over 21. Plus, here x is 2, so 2 times 1, this will be 3 over 21, plus this is 2 times 2, this will be 4 over 21, and finally we have 2 times 3, and this will be 5 over 21. And so when I look at this, let's see, the top is, this is going to be 2 plus 6, okay, plus 12, plus 6, plus 16, and then finally plus, this is 30 over 21. I think I'm out of the screen here. Let me rewrite that. So it was 2 plus 6 plus 12 plus 6 plus 16 plus 30 over 21. And when we add those together, there's 46, 52, 54, 64, I think it's 72 over 21. 3 are going to both of that. So that's 24 over 7. That's what we get. 24 over 7. Okay, now we need to compute the expected value of x. It is equal to the sum, as x runs from 1 to 2, sum, as y runs from 1 to 3, of y times x plus y, dx, times x plus y over 21. And that's going to be equal to, so we'll let x be 1 to start off with, so we have 1, and then when y is 1, we have 2 over 21. When x is still 1, we're adding, and then here this will be, y will be equal to 2, so we have 3 over 21, plus 1, and here this will be 4 over 21, plus, now when x is 2, and y runs from 1 to 3, we have 2 times, so this will be 3 over 21, plus 2 times 4 over 21, and then finally we have plus 2 times 5 over 21. So this ends up being 2 plus 3 plus 4 plus 6 plus 8 plus 10 over 21. And so we end up getting 18, 24, 28, 31, I think 33 over 21. And that is 11 sevenths. And finally, the expected value of y is going to be equal to sum as x runs from 1 to 2, sum as y runs from 1 to 3 of y times x plus y over 21. And that's going to be equal to, so when x is 1, we're going to get 1 times 2 over 21. Y is 2, now we have 2 times 3 over 21. Y is 3, so it's 3 times 4 over 21. Now when x is 2, we get plus, y would be 1, so we'd have 1 times 3 over 21 plus 2 times 4 over 21 plus 3 times 5 over 21. Okay, and that's equal to, let's see, this is going to be 2 plus 6 plus 12 plus 3 plus 8 plus 15 over 21 is 23, 26, 28, 38, 44, 46. 46 over 21 is what I get. And so here, the covariance of x and y in this case is equal to the expected value of x times y minus the expected value of x times the expected value of y. That's going to be equal to, so it was the expected value of x times y was, I think it was 24 over 7 minus, here this expected value of x we calculated just a few seconds ago was 11 over 7 times, here this was 46 over 21. I think when you do this, you end up getting minus 2 over 127. So the covariance can be negative, that's okay. And that's an example of it. Next thing I want to list is some properties. There's some properties of covariance. So here's 4 things I'm working on. One, maybe something you noticed, but the covariance of x with x, it's easy to show, is equal to the variance of x. Matter of fact, all of these are pretty much easy to show. The second thing is that the covariance between x and y is equal to the covariance between y and x. A third fact is that the covariance of a constant times x with y is equal to that constant times the covariance of x with y. And the fourth one, right here, is that the covariance of x with y plus z, that's equal to the covariance of x. Maybe I'll write that on the other. Sorry. So the last property was that the covariance of x with y plus z, that's equal to the covariance of x with y plus the covariance with x with z. So I said these were easy to prove. We'll go ahead and do that. And the first part, part one, was that the covariance of x with x, we want to show that's equal to the variance of x But that's nothing more by definition than the expected value of x minus the expected value of x times x minus the expected value of x. And that's equal to the expected value of x minus the expected value of x to b squared. And that is the definition of the variance of x. It's that easy. So that's part 1 done. 2, it's very easy as well. The covariance between x and y, we want to show that's equal to the covariance between y and x. Well, that's equal to the expected value of x minus the expected value of x times y minus the expected value of y. And we can just reorder these to be equal to the expected value of y minus the expected value of x, expected value of y, times the x minus the expected value of x, and that is the covariance between y and x. So that means that one. Thirdly, we want to show that the covariance of c times x with y is equal to c times the covariance of x with y. Well, what it's going to be equal to, first of all, is going to be equal to, I'll use the formula this time, I believe. It's a quicker way of doing it. Yes. So this is equal to the expected value of the first guy, c times x, times y, minus the expected value of the first guy, which is c times x, times the expected value of the second guy, which is y, by the formula. But c is a constant, so we can pull it out. So c times the expected value of x, y, minus, here I can pull out the c from this expected value, x times the expected value of y. There are two terms up here, both of them have a c, so you factor out the c, you got the expected value of x times y, minus, this is the expected value of x, times the expected value of y, and indeed that's nothing more than c times the covariance of x with y. Okay, that's what we wanted to show. So that's that one. And fourthly, if we're trying to show that the covariance of x with y plus z is equal to the covariance of x with y plus the covariance of x with z, but this is by formula going to be equal to the expected value of x times y plus z minus the expected value of x times the expected value of y plus z. And that's going to be equal to the expected value of x times y plus x times z minus the expected value of x. And here, the expected value of y plus z is the expected value of the sum, which we know to be the expected value of y plus the expected value of z. And here, the expected value of the sum is the expected value of the first guy plus the expected value of the second guy minus the expected value of x times the expected value of y, distributing this expected value of x, minus the expected value of x times the expected value of z. And then you just kind of group terms together. This guy and this guy makes the covariance of x with y. This guy and this guy makes the covariance with x and z. Let me write that down. Covariance of x to z. That's what we're trying to prove. That's that proof. Okay, lastly, I think we'll do examples of this fact later. We're going to say the fact and prove it. If we let x and y be continuous, random variables, so they're continuous, with f of x being the PDF of x and f sub y of y being the PDF of y. Okay. Then we're going to suppose x and y are independent okay. Then the PDF of, okay, wait a minute, it's x plus y, we consider that one random variable, is f sub x plus y acting on something, let's call it a, and it's going to be equal to the integral from minus infinity to infinity, okay, of the PDF of x evaluated at a minus y times the PDF of y evaluated at y, and then dy. Okay, that's going to be the answer to it. Let's prove that. So the proof, okay, so let's start off with let x and y be independent. Okay, we'll start off that way. And continuous random variables. Okay. And so here, if we start off, note the CDF, cumulative distribution function of x plus y is, so here it will be f of x plus y acting on, let's say A, okay? And what is that? That's equal to the probability that x plus y is less than or equal to A. And we can think of this as a double integral. This is the double integral of the region where x plus y is less than or equal to A of the joint PDF. But since we have independence, okay, and ladies and gentlemen, let's come over to the side here. And let's think about this region that we're integrating over. So here, maybe this is A, here's A. We have y is equal to, this will be a minus x, so when x is 0, okay, y would be equal to a. When x is a, y would be 0, so we're looking at this. Okay, we end up integrating over this region. This is where x plus y would be less than that, and so you notice that if a is positive, 0 plus 0 is going to be less than that. So it's that region. Okay, so this is going to end up being the integral. So the y values, if I look up here, the y values, they run from minus infinity up to infinity over this whole region. And then the x values for a particular y, let's say from here, let's call it this one. They run from minus infinity up to this line. And so that line, in terms of solving for x, is a minus y. And here this will be f of x sub x times f sub y of y dx dy due to the independence. I can rewrite the joint in that fashion. And that multiplication. Okay, that's correct. And then what we're going to do is notice, well, let me go back just for a second. What we're going to do here is notice, I don't like this A, where it goes, is that when we're integrating with respect to x, the f's of y can be pulled out. So that's the next thing we're going to do with the first integral. We're almost done. So that's equal to the integral from minus infinity to infinity. Here, this is the integral. I'm pulling out the f's of y. This is the integral from minus infinity to a minus y of f sub x of x. Then I have dx and then dy. So we do this first integral, and what we see is that's the outer integral from minus infinity to infinity. F sub y of y. Well, look just right here. That's nothing more than the CDF of x evaluated at a minus y, and then dy. Okay? So that's what, if you recall, f sub x plus y of a is. So if we take the derivative with respect to a of the CDF, that's going to be the derivative with respect to a from minus infinity to infinity of f sub y, f sub x of a minus y, dy. And I'm telling you, you can bring that derivative inside the integral. I'm not saying why, but you can. Here, this is f sub y of y, and then this will be the derivative with respect to a of the CDF, dy, and that's equal to the integral from minus infinity to infinity, f sub y of y, and the derivative of the CDF is nothing more than a ddf. And that's what we were trying to get, and so that proves right there, that proves the result. Ladies and gentlemen, that's enough for this session. We'll start by doing examples, an example of where we use this fact. Thank you very much.